Hi, welcome back to this video. We're going back in HYSYS, and in the last video we saw how we actually can remove SO2 and NO2 from the flue gas mixture so that it doesn't get trapped when we try and use let's say our MEAmine solution. So we washed up most of the SO2 using water, NO2 as well, to a very low concentration. And we're just going to assume that's okay. So the next thing is we'll probably want to extract the CO2 out from the flue gas mixture. So how are we going to do it? Well, firstly we want to use this thing called amine gas treating, and there are a few ways we can actually do amine. I mean, the idea of amine gas treating is basically we pass the flue gas into an absorber with some amines, and the amines will actually absorb some of that CO2, and you can go to a stripper where there is actually the CO2 gets stripped out when you heat it up. And so we want to see how we can actually get this done on HYSYS, and we want to compare some of the amines as well. So there's basically a few kinds of amines I want to explore, 4 in total. First being monoethanol amine, or MEA. The max percent will be about 28%. This is from digital refining, of course. Secondary amines such as diethanol amine, they can come at 35 weight percent. And tertiary amines such as methyl diethanol amine, MDEA, which can come at 50 weight percent. So and what's more, this tertiary amine, MDEA, it says it's not prone to degradation and corrosion is low, and reclaimer is unnecessary. So basically it's pretty good. And the other one, the last one, is of course there's a mixed solvent, and which we are not going to touch. But there's one more I want to explore. It's called diisopropanol amine. This is diisopropanol amine. Okay, so this is it's a secondary amine, and secondary alkanol amine. So it has these two propanol chains at the side. So we want to see which of these is most suitable and for the treatment of our flue gas. So let's try the MEA one first. MEA and water. So again, the max concentration, we are just going to go straight for the max. Alright. Okay, it looks like there's only one of these amines down here. We'll need to add some of the components into the system. Okay, so diethanol amine. Okay, HYSYS is lagging. Fear not. Okay, so monoethanol amine, diisopropanol, diiso-PA amine. So yeah, that's what we want. I'm gonna save this. We're gonna shift it. So says the component list for acid gas contains an unsupported amine combination. So it says select supported amines to replace with, and then it says current amines in the component list. So basically what it's saying is that you can only pick one of the many in maybe in each HYSYS simulation. So we want to maybe we start with monoethanol amine. Then we'll have to open I think we will have to open a few other HYSYS files in order to do a comparison. So no, we don't want it in holding mode. I'm just gonna let it converge. So we have this one, MEA and water. So I'm just gonna save this as the MEA base case, monoethanol amine base case. Okay, so let's do 20% MEA by weight, mass fraction 20%, and we'll do the remaining being water, and you just press OK, and let's have it come in at about 30 degrees, or maybe 40 or 45, 40 degrees, pressure about 200. Okay, so the molar flow, we'll try to have a 1-to-1 with the CO2. Okay, let's just give it an arbitrary one first. So let's try and put 1000 so that all our MEA is pretty much saturated. Okay, so mole flow, we have 68.66. So we want to absorb about 225. So we'll have to increase it by about 3 times. 206, because it's a 1-to-1 thing. Yeah? So if I'm not wrong. So let's increase it a bit more, 35. And let's put this into an absorber tower. Let's just try that. Absorber tower, that's under columns. You go to this absorber subflow sheet, and there's we'll name it the MEA absorber. Okay. What goes in on top is the MEA and water. What goes at the bottom is the washed flue gas. So, okay. Bottoms will be rich amine. Overhead will be scrubbed gas. So basically scrubbed meaning to say there's no more CO2. Top stage pressure, we'll give it 101.3 or 102, basically atmospheric. At the bottom we will give or take 130, 150, yeah? Give or take. Temperature estimate, we are not going to do anything, so let's run the thing to see whether it converges. Okay, HYSYS is lagging again, so let's just wait. So yeah, it's converged. So let's see how much CO2 has actually gone into the rich amine. So take a look at the mole flows. We see that only 94 so-called 94 kg mole per hour has been absorbed. Okay, I probably want to reduce this to about 110, so it's not so. Yep. So you probably need to use a lot more amine. Okay, more amines needed, so let's double that, maybe triple that to just slightly less than triple, to about 8000. Let's see whether that's enough. Okay, so the CO2 is about 128 kg mole per hour. We need a little bit more. Yeah. So what we can do, either we increase the amine flow rate or we increase the number of absorber stages. I'm just going to do that to 15. So the bottom pressure we'll put at 160. Yeah, it should be 150, sorry. You have to use some kind of special towel packing in order to, yeah. Okay, so let's take a look. By increasing the number of stages, we have actually increased the amount of CO2 being absorbed. So not too bad, that actually looks pretty good. So yeah, and let's look at our scrub gas. Mole flows, there's some H2O coming out, but a fair bit of the carbon dioxide is also leaving the system. So what can we do? Well, the thing is that we can either pressurize this gas and then pass it through yet another absorber, or we can do in parallel or series. So that there are a few ways we can actually use this washed flue gas to be extracted from the amines. So right now I'm just going to try the series configuration to try and absorb the amines better. And usually we don't exceed 15 number of stages for, let's say, a packed tower, because otherwise it can get too high. I mean, that's just a general rule of thumb. Doesn't have to always be followed, but there are always cost considerations. So I like to keep it at less than 15 or 20. Okay, so let's try the series configuration. So I'm going to do this. So I'll name this MEA Absorber 2. Okay, so what I'm going to do, I'm going to split this stream up into two. I'm going to split this stream up into two. Okay, so I'm going to hold. I'm going to break the connection here. So, gas splitter, flue gas splitter. Okay, so let's go one to here, first tower, and let's go. The other one goes to the second tower. So I'm just going to call it second tower. Now, of course, the capital cost is going to increase, but if it gets the job done, then why not? Yep, so let's take a look. We're going to have a 50-50 split. And this rich amine will be going to the top here. Okay. So, scrubbed gas. 2. And richer amine. Okay. Okay, I'm going to call this scrubbed gas 2 again. Scrubbed gas 2. Okay, let's go next. Top stage pressure 102 again. And the bottom stage will be about 150. And we go next. So I'm not going to give you temperature estimates, so let's try and run this column. Active first, reset, run. The other one has to do the same thing, so let's give it 15 stages again, and run. So these two columns has been converged. So let's take a look at how much amine has been absorbed overall. How much CO2 has been absorbed overall, rather. Okay, 209. That's a lot better. So let's see whether we can play with the split ratio to the first tower. See whether it does any difference. (211). Okay, so probably we might want either a third tower or just increase the MEA flow rate. So let's increase it to about 10,000. Okay. Oh, so yeah, increasing doesn't seem to do much. So looks like we'll have to do something else. Either we have a third tower or increase the number of stages per tower. So I'm just going to get one more tower. And probably we'll need to install some pumps here because there's pressure drop we haven't accounted for. So let's raise water out. So let's split it again. Third tower. And instead of creating one from scratch, I'm just going to clone the second tower. Let's clone. so that kind of saves time. So third tower will go to the bottom. .3. Okay. So let's see whether that works. So let's run this fella. So I'm just gonna call it scrub gas 3. Okay, just nice. Richest amine. Okay, so it seems that doing the towers kind of do the trick. Okay, I mean you can always increase the amine flow rate, but that may have some trade-off. So the more amine you use, the more you might have to replace, and not only that, I think maybe there's a higher stripper reboiler duty. I mean, all of these things can add up later on. Okay, but this is somewhat of a workable system. Okay, so that's somewhat of a workable system. Alright. Alright, so now this scrub flue gas is going to be what we don't want. We don't need it anymore. So we're just going to leave it be. I'm just going to put it together on some top here. So the 3 absorber towers. So we have this very rich amine, which we will now need to heat up in order to get a good to help strip the CO2 out of this amine. So we need to heat it up to about 117 degrees C. And where can we find that heat from? Well, conveniently, we have some of these heat exchangers previously that we were getting from here 265 degrees C down to 70, and another one here 113 down to 70. So we could take a look at these, see whether some of these can be used. Okay, so let's do some we can do some heat integration, but maybe we'll do that later. Yeah, so I'm just going to put a heat exchanger. Going to put a heat exchanger, or rather a heater, because we want to do the heat integration later. So we're going to heat it up maybe to 17, richest amine hot. So we put the temperature at 117 in order to prevent degradation. We want to keep it below 120 usually. So amine energy. So delta P, we'll give it 50 kilopascals, because that's actually not too much. Okay. Let's just tidy up. Alright, so this is how the tower is going to be. So this is a very hot amine, so it's partially been vaporized already. So what can we do? I think part of it can be heated up even more. Okay, so the vapor is already what we can send. It's already, we can separate it out. Actually, most of it has been vaporized, in fact. So take a look at the composition and the vapor phase and the liquid phase. The liquid phase is mostly monoethanol amine. So and it's going at about 100 kilopascals. Okay, we should reduce it maybe to 35, because it doesn't make sense. Okay, so this richest amine will be fully liquid. This one will be partially liquid and gas. And this amine energy, that's a lot of energy. You can see down there, 100,000 kilowatts in fact. So you can see that yeah, probably the heat supply will need to come from some steam or something, but you can see that it's going to take up a lot of energy. So heat integration is going to be very important later on. So this all these things, the energy usage, will be sort of things we need to look out for later on. But for now, let's just put a stripper column first. Stripper column. So sometimes you can use a distillation column straight. Just pull out distillation column, the top left one. Okay, so I'll put this as, so these are the things you need to label. So stripper column. Okay, and here we need to put the inlet streams. So hot amine will come from the top, richest amine hot will come from the top. We will have a full reflux condenser, maybe either that or partial condenser. We can actually just edit that later. So we have gas overhead, and we have water, maybe some water that we can condense. So stripper duty is here. Condenser duty, reboiler duty, and lean amine. Okay, so let's take a look. Okay, so we go next. So regular HYSYS reboiler, condenser pressure, how much is it? We'll give it about atmospheric thereabout, or in fact slightly higher, maybe 102. Pressure drop across condenser, usually it's pretty high, so we'll give it 100. Reboiler is also 100, so the bottom needs to be pretty high pressured. So 100 plus 100 plus 100, so maybe you have about 300. Pressure reversal, what does that mean? Basically, it means that the bottom pressure is lower than the pressure at the top. The reboiler pressure is lower. I mean, there are stages in the bottom part of the tower that have higher pressure, lower pressure than stages at the top of the tower, which doesn't make sense. So you need to do a bit of this. We'll just increase the reboiler pressure, and we go next. Reboiler estimate, no, we're not going to give estimates. Reflux ratio, let's give it about 1. Vapor rate, we want CO2, so we give it about 250 maybe. Liquid rate, we'll try very little. Okay, so we're just done. We'll try and run the tower. So richest amine is going below the pressure. Okay, so now we have this thing where we have this equilibrium error thingy. It doesn't seem to oscillate. So this is what is known as a heat spec error, and a lot of problems do arise because of this. But do not worry, we'll try and learn how to troubleshoot this heat spec error. Now, first thing first, we need to do something. We need to increase this pressure from 115 maybe to whatever the tower requires. So usually we want to avoid the use of compressors, so we increase the pressure before we send it to the heat exchangers. We increase pressures using pumps rather than the compressor. So we want to increase pressure using a pump first. So I'm going to use an amine pump. Let's go and call it amine pump. So richest amine pressure, pump duty. There you go. And let's bring it up to about 400 kilopascals. Let's active. Let's draw it back to the heat exchanger. Okay, so it's 365 kilopascals now. So now you see this thing that's oscillating back and forth, and it can't really converge. So let's stop. there are two things I want you to take note of. Okay, firstly, notice that it's oscillating, so probably the solution isn't being reached. So the HYSYS actually uses iterations to try and solve this stripper column. So if it's oscillating, it's probably meaning that when you iterate, the step size might be too big for you to reach the column. So let me give you an illustration on Paint. Okay. So let's say you have this this curve, and there's an intersection point over here. All right. So let's say this is the place where you have the convergence. Okay. So HYSYS maybe will initially guess something like here. Then after iteration, after the step size of iteration, it will try to jump to here. But you see, this is what you see here is probably a minimum step size. So this is the minimum step size. So at the second instance, maybe HYSYS will be jumping here. So it's missed the solution again. So HYSYS will try to re-guess, and maybe you'll end up somewhere here. So the effect is that you keep oscillating back and forth because the step size is too big. So the solution is to reduce the step size to a new minimum so that you can start to converge. That could be one of the common problems encountered in the MEAmine system. So how do we actually get this done in HYSYS? Well, I'd like you to go to the solver tab, and you look at this thing called damping factor. This damping factor is actually what determines the step size. So if we reduce the damping factor, let's say from 1 to 0.1, and we try and run the simulation again, let's see what happens. So now your column converges with a damping factor of 0.1, and basically you have the column conversion. So this is one of the workarounds for the non-convergence of columns. So in fact, you have a lean amine temperature of about 140 degrees C, which you do not want at all. And so you probably have to do something about that later on. But anyway, that is one of the things to help you do this damping factor thingy. So yep. And let's look at the CO2 we are harvesting, 155. So we kind of need even more CO2. So that's going to be an issue we will need to solve, but we are fast going to about 30 minutes. So we'll need to stop the video soon. So anyway, how are you going to determine the damping factor? That's the last thing I want to talk about. Basically 0.1 is a good guess, but if you're not sure, let's try reset and running at 1. So again, it doesn't quite do its job. So if you're not sure, you can let HYSYS try and guess the damping factor for you. So you can, instead of using the fixed solver, you can use the adaptive solver. We can do a reset and run. So after that, HYSYS will help you to guess the damping factor, and now it converges at the damping factor of 0.7. So it will give you more or less the same result. And that's how you converge columns and prevent the heat spec error from happening, especially for amine towers. Okay, so thanks for watching. I'll probably see you guys in the next video. See ya.